Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. All right, tonight, this video, I'm going to do quiz 6 review. Remember, this Wednesday, I will be giving quiz 6 online, and you download it like we've done the other quizzes, the PDF file from Blackboard assignment area. And Wednesday morning, 8 a.m. or earlier, probably a lot earlier, I will send out an email to all of you with the password for quiz 6. Now, in another video, I'm going to talk about test 2 and the ACS final exam. And also another video, I'll be going through test 5 answers. But this video, I want to go through the review for quiz 6. So let's do that. All right, what you see on the screen is available in the lecture section of Blackboard, cleverly named Chem 1211 Quiz 6 Review. I have it both as a Word file and a PDF. All right, Quiz 6 deals with acids and bases. So the first thing you should know is what's a Bronsted-Lowry acid? And that's any substance that can donate a proton H plus to another substance. Another way of saying that is a proton donor. Now, what's a Bronsted-Lowry base? That's any substance that can accept the proton from another substance, otherwise known as a proton acceptor. So acid donates a proton, base accepts a proton. Now, you should know the chemical formulas for these very important acids and bases. For acids, you should know HCl, hydrochloric acid, H2SO4, sulfuric acid, HNO3, nitric acid. They're all very strong acids. Now, bases, sodium hydroxide, NaOH, potassium hydroxide, KOH, and ammonia, NH3. These are all very strong bases. Let's go back here in case you're writing it down, but you can also go look at this file. Again, here are my acids, HCl, H2SO4, HNO3. Here are my bases, sodium hydroxide, NaOH, KOH, NH3. Now, while I'm here, one base that you should be aware of is sodium bicarbonate. And sodium bicarbonate is found in baking powder. Now, it turns out water is a very interesting chemical. Yes, it is a chemical. And a small amount of water can react with itself to form ions. And notice it's an equilibrium, and the equilibrium is mostly to the reactant side, but enough forms H3O plus hydronium ions and OH hydroxide ions. And the ionization constant for water, Kw, I wish it was named after me, those are my initials, but it's not, is the concentration of H3O plus times the concentration of OH minus. That's what the brackets mean, moles per liter, equals 1, or actually it's 1.0, times 10 to the minus 14th at room temperature. Hint, you should know this. You should memorize this. Again, the hydronium ion concentration times the hydroxide equal 1.0 times 10 to the minus 14. Now, when we talk about solutions, and we're talking about aqueous solutions, there are three types of solutions in acids and bases. Acidic solution, a solution in which the concentration of the hydronium ion is greater than the concentration of the hydroxide. Another way of thinking of it, the hydronium ion is greater than the hydroxide concentration. That's an acidic solution. Your stomach is acidic solution because of that. There's also acid, hydrochloric acid in there. Now, basic solution, hydroxide ion concentration is greater than the hydronium ion concentration. And this is a basic solution. And finally, a neutral solution, the hydronium ion concentration is equal to the hydroxide. Now, this is pretty hard to visualize and work with. And someone came up with, one of these days I'll look it up who did it. I think it was a group effort, the pH concept. And the pH concept is a pH scale. It's a scale of small numbers that are used to specify the hydronium ion concentration in aqueous solutions in water. And the concept is pH equal minus the log of the hydronium ion concentration. And once again, it's time to be subtle. And you should know that. Now, for my tests and quizzes, a special little gift is if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. Again, my gift to you, if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. Now, one of the most important things I'll teach you this semester is the pH scale. And this one you should really know. And at pH 7, you have a neutral solution. Anything above 7 is basic, and anything below 7 is acidic. So if you have something that's pH 2, it's acidic. If it's pH 13, it's very basic. And the lower the pH, the more acidic it is. The higher the pH number, the more basic it is. It's a logarithmic scale, so each number is a power of 10 difference. Now, an important thing that plays a role in our body are buffers. And buffers are a solution that resists major changes in pH when small amounts of acid or base are added to it. So if I have a buffer solution, I put a small amount of acid or base, the pH stays the same. Again, if you add a small amount of acid or base to a buffer solution, the pH stays the same. Now, the final thing I'd like to talk about, actually a little, not the final, but the final concept in this are titrations. At neutralization, when the pH is 7, and you use a pH indicator like phenolphthalein, when it changes color, that tells you you've reached a boundary of 7. At that point, for monoacidic bases and acids, moles of acid equal moles of base. And you can use this simplified formula that I created: milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And in a problem, you'll be given this, and then either the molarity of acid, and you're going to try and find a base, or you're given molarity of base, and you're going to try and find the molarity of acid. And that's the stuff for test quiz number 6, other than one thing I do want to do. Is let's briefly go through a couple of key problems in chapter 14, practice problems. And notice number 3, your job is to identify things as acid base, and I threw in sodium chloride, that's a salt, and you should be able to do that. Next, let's look at number 4. If the solution has a hydronium ion concentration of 1.0 times 10 to the minus 3, what is the pH of the solution? And is it acidic, basic, or neutral? So you're trying to find the pH. You're given the hydronium ion concentration. Excuse me, 1.0 times 10 to the minus 3. And pH is minus the log of the hydronium ion concentration. You put it in. When it's 1.0 times 10 to the minus x, the pH is x. In this case, x is 3. And notice I have here the scale 0, 7, 14. 7 is neutral, below 7 is acidic, above 7 is basic. Well, 3 is less than 7. So this is an acidic solution. Now let's look at number 7. If a solution has a hydroxide ion concentration of 1.0 times 10 to the minus 3, what is the pH of the solution? And is it acidic, basic, or neutral? Well, you need 2 steps. pH is minus log of the hydronium, H3O+, but we're not given that. So in the first step, you have to solve for hydronium ion concentration, H3O+. How do you do that? Well, remember KW, yay. No, it's not after me, I wish it was. But anyways, hydronium times hydroxide equal 1.0 times 10 to the minus 14. We want to solve for hydronium. Well, anything divided by itself is number 1 and is gone. So I divide this side by hydroxide concentration, OH minus, But whatever I do to one side, I have to do the other, and I did. This cancels out, so hydronium, H3O plus, equals this. Put in the numbers, and that's 1.0 times 10 to the minus 11. Are we done? No, that's not the pH. Second step. Ooh, the 2 fell off there. Sorry. Solve for pH. pH, you should know, minus the log of the hydronium ion concentration, H3O plus. In this case, we just figured out H3O plus concentration is 1.0 times 10 to the minus 11. When this is 1.0 times 10 to the minus x, the pH is x, in this case 11, this is acidic, neutral, and basic. Anything above 7 is a basic, and 11 is above 7, so it's a basic solution. And here I ask, if you add a few drops of concentrated NaOH, what happens to the numerical value of the pH in a beaker of water at pH 7.0? Well, if you add a base, the pH goes up. If you add an acid like H2SO4, the pH goes down or decreases. For buffer, they say the same. Now let's look at number 12. If you have to add 1.35 times 10 to the third milliliters of a 1.53 capital M, and remember, capital M is molarity, NaOH solution to neutralize, and that's the key thing, neutralize 1.87 times 10 squared milliliters, that's ml, of an aqueous HCl solution. What is the molarity of the HCl solution? Well, we're trying to find the molarity of HCl, MHCl. It's an acid. We're given the milliliters of the base and its molarity and the milliliters of acid. At neutralization, moles of acid equal moles of base. And as I developed for you for a monoacidic and basic acid, milliliters of acid times molarity acid equal milliliters of base times molarity. Now, we want to solve for molarity of HCl, so we want it alone on one side. How do we get rid of milliliters of HCl? Divide by it. Anything divided by itself becomes the number 1. But whatever we do to one side, we have to do to the other. And I did. And this cancels out, and we're left molarity of acid equals milliliters of base times molarity of base divided by milliliters of base. Notice milliliters cancel out, we're left with molarity. Put the numbers in. Remember, use proper significant figures, 3, 3, 3, so I have an answer of 3. And that's how you do it. And I have some other examples for you to look at. And what I'm going to do, since I'm going to separate 2 videos, the quiz 6 review, I'll put public, and then I'm going to do a separate video for quiz 5 answers, and also some stuff about the final I'll have unlisted private that I'll send out to URL. So for this part of the video, I'm done. And you know what I'm going to do. It's time to say "Gang gesund," which is Yiddish for going hell. And bye now. Bye now. Stole that from Granny and the Beverly Hillbillies. Bye.